In this video, I'll define exactly what is meant by scalar multiplication. I'll define this operation between a vector and a scalar, and we'll take a look at a few examples of scaling vectors. So first off, scalar multiplication. So again, given a scalar, and again in this class it's a real number. By the way, in later more advanced math classes, you might scale by complex numbers. This might be important to an electrical engineer. However, in this class, we are just sticking with real numbers. So I'm going to scale a vector v. So my scalar c, my vector is v, and produce a vector cv. Right? So take a scalar c, take a vector v, and I combine these two things into cv. I'll draw an arrow above the whole thing. cv is a vector. So take a scalar, take a vector, output a new vector. That is the scaled version of v. Now its length will be the absolute value of c. So it's possible I scale by a negative, which is going to, as I talked about in the last video, is going to flip the direction. That's not going to change the magnitude at all, if whether it's positive or negative. So that's why this is an absolute value. Times the length of v. So let me just look at a really quick example here geometrically. Let's say this is u, and let's try to draw 2u here. So 2u has the same direction as u, but its length is 2 times the length of v. So I've tried to draw it that way. In this way, it has the same direction, but its length is twice that. So that's what 2u represents. At the same time, I can also compute negative 2u. And one way you can do the negative is just swap. As I told you, the position of the vector doesn't matter. And so I can swap the head and the tail of 2u to come up with negative 2u. So there I've tried to draw negative 2u. Has the opposite direction as 2u, but the same length. So again, that's where this absolute value is coming from. Absolute value of my scalar. That's telling me the length. And then whether it's positive, negative tells me whether or not to keep the same direction as the original vector or switch it. So that's two things that vectors do: scale and possibly change the direction to the opposite of what it was if this is negative. Right, so that's what this is talking about here, is determined by the sign of c. If c is positive, it has the same direction as v. If c is negative, it has the opposite direction of v. You might ask, what if c is 0? So that's the scalar 0. Then, well, 0 scalar works exactly how it does when you operate just with real numbers. If I take 0, the scalar, and multiply it by any vector v, what I get is the 0 vector. So that is, I've reduced its length to 0, and therefore it does not carry a direction anymore. If the length of a vector is 0, there's no direction to it. And so this is a special property of the 0 scalar operating on a vector. One bit of terminology here: two vectors are parallel if they are scalar multiples of each other. So these three vectors here, these are all scalar multiples of each other because they're scaled versions of u, and so we say they are parallel. So that's what's meant by parallel. All right, so that's a bit about scalar multiplication. Let's get a little bit more comfortable with this by looking at an example. All right, so in this example, and you can see this is in the book, we're going to work through this together, but you can do this on your own if you'd like. And if you'd like, just pause the video here, figure these out as best you can, and then if you need some help, you can watch the rest of the video. So let's see, the following vectors in terms of u and v. So PQ, remember what this means. P and Q are points in the plane, and there's an arrow above them, so this indicates that PQ, that vector, is this one, whose length is the distance between P and Q, and direction is determined by the relative position of the points P and Q. So this is the vector PQ. Now our goal here is to write PQ in terms of u or v. Well, u goes over 1, right? If you can see these lines here, u goes over 1, and it doesn't move up or down at all. Same as PQ, goes over 1, doesn't move up or down at all. So u is the same as PQ. This is exactly the same as u. So I didn't need to scale it or anything like that. It's just u. All right, let's take a look at another one. How about QP? So QP is going to be this vector here. I got to change I'm zoomed in too much, and that is making it not look very good. Let's see, make this smaller. So QP, the vector that goes in the opposite direction as PQ. So this is now QP. And again, it goes now not to the right one, but rather to the left one. And it doesn't go up or down at all. So this is negative u. It's also the same as negative PQ. In general, that's going to be true if we switch the head and the tail of a vector given by 2 points. We'll end up with the negative. QR, let's take a look at QR here. How about I'll use red for this. QR would be this vector going up like here. Again, here's the head and the tail. And let's see, so u, it doesn't look like u at all. It does look, however, that v, look, I've traveled v, and then I did v again. I went up to this next line up here vertically, and up to the next one like that. So this is now 2v. This is the vector QR, which is 2v. Scaled version of v. And let's see, one more RS. Let me find a different color here. What have I not used? Let's use this sort of light blue here. So RS is this vector coming this way. Let's see, I'm going 1, 2, 3 over to the left. U just goes 1 to the right. So this is going to be negative 3u. And that's RS. So that's the idea. That's how we can take a vector and sort of make it referenced to another vector. We can say that it's a scaled version. It's parallel to it. So for example, u and PQ, these are parallel vectors. In fact, they're equal vectors. But also u and QP, these are parallel vectors. QR and V are parallel vectors. RS and U are parallel vectors again because they're scalar multiples. Of course, I can't say though that QR is not parallel with U. It's not a scaled version of U. So that's a bit about how scalars can operate on vectors and produce new vectors. Scalar multiplication. This is one of our pieces of bread and butter for working with vectors. In the next video, we're going to look at adding vectors together. I'll see you there.